Hello and welcome to WinXAS Tutorials. This time I want to start talking about EXAFS analysis. I will be covering the basics of EXAFS analysis in 2 tutorials, probably followed by several more about specific examples and difficulties you may encounter while analyzing your own data. As always, the WinXAS software and the XAS data I will be using in the hands-on session can be obtained from the WinXAS website. Structural information about a sample comes from analyzing its X-ray absorption fine structure in either the K or the R space. Measurement and Fourier transformation reduces the three-dimensional structure of the sample to a one-dimensional radial distribution function. Therefore, a structural model needs to be used to calculate a theoretical EXAFS function and compare it to the experimental function. By changing the structural model and minimizing the difference between theory and experiment, characteristic structural parameters can be obtained. This is the EXAFS function commonly used to calculate a theoretical EXAFS chi of k. As briefly mentioned in a previous tutorial, this function requires 2 sets of parameters. One set corresponds to the model structure, and those parameters are varied in the refinement procedure. The other set corresponds to the scattering behavior of the various atoms in the model structure and needs to be obtained from either theoretical calculations or experimental reference spectra. We want to start with extracting experimental phases and amplitudes from reference spectra and use them in EXAFS simulation and refinement. This procedure involves back transformation of a certain range of the Fourier transformed chi of k. The back transformed range must contain only a single shell in the model structure, which limits this approach to the first shell in most cases. However, it also reduces the number of parameters in the refinement and makes it a good starting point for talking about EXAFS analysis. The choice between using experimental or theoretical phases and amplitudes is being made in the EXAFS simulation box. Because experimental phases are mostly used for simulating or refining the first shell in the pseudo-radial distribution function, both selection of phases and setting starting parameters is easier with considerably less options to choose from. For instance, multiple scattering shells and the question of significant higher shells do not need to be considered. On the one hand, in most cases, the EXAFS refinement will be performed in the R space to a selected region of the radial distribution function. Experimental and theoretical EXAFS chi of k in the k range are only shown for comparison. While in theory, the refinement could be carried out with a back transformed chi of k in the k space, this is not necessary and rarely done. On the other hand, the EXAFS refinement can be carried out to 2 pseudo-radial distribution functions using different k weightings. While of restricted use for a sample with only one type of backscatterer like copper metal, it may prove beneficial for structures with light and heavy backscattering atoms like transition metal oxides. After any EXAFS refinement, it is of paramount importance to evaluate the resulting parameters. Because structural parameters affect either amplitude or frequency of the theoretical EXAFS chi of k, parameters can be heavily correlated to a point where the results are entirely arbitrary and useless. So, what tools are available for evaluating parameters? First, the number of independent parameters as introduced earlier. However, Parameters may be heavily correlated, even well below this number. Second, standard deviation and correlation matrices are calculated by the least squares refinement procedure and can be of help identifying problematic parameters. Even better suited and with a more meaningful results are confidence limits. In WinXAS, confidence limits are calculated by varying a certain parameter and keeping it invariant in the subsequent full refinement. Within the confidence limit, the corresponding parameters can be varied while maintaining 95% of the original fit residual. A large confidence limit readily identifies a strongly correlated parameter. Confidence limits and F-tests are described in the manual with references for more details. Shown here is an example for a first shell refinement of the pseudoradial distribution function of copper metal. Structural parameters are coordination number, distance, disorder parameter or Debye-Waller factor, and the E0 shift. Calculated confidence limits are in the range of a few percent of the original values. F-test parameters are all zero, indicating a refinement with largely independent parameters and reliable results. Coming next is the hands-on session. Objectives will be extracting experimental phases and amplitudes for the first copper-copper shell in the Fourier transformed chi of k of copper metal, and using these to perform an EXAFS simulation and refinement to the experimental spectra of smaller copper clusters. The spectra used are included in the tutorials data folder, which can be obtained from the WinXAS website. Let's get started and open the experimental EXAFS chi of k of copper metal. To save some time, we skip the data reduction and start directly with the extracted EXAFS function. First step is the Fourier transformation. Bessel window, we leave all those settings, and okay, we get the Fourier transformed chi of k, the pseudoradial distribution function of copper metal. So next step is now we want to back transform only the first shell. For this we go to EXAFS menu again, Fourier transform again, and the program recognizes the Fourier transform already active, and so it assumes that you want to back transform. For the back transformation, you need to select the range that includes only the first shell, only the range that you want to use for the back transformation. Here it's best to go from minimum to minimum and define by this the range that includes the first shell, only the first shell in the structure of copper metal. Click on OK and on OK, and this is the back transformed first shell chi of k of copper metal. So next step now, from this we want to calculate the experimental phases and amplitude. This is again in the EXAFS menu, phases and amplitude. We want to extract modified, what is called modified phases and amplitudes here, where we actually need to input the crystallographic values for the first shell in copper metal. And that can be used then, or those phases and amplitudes then can be used for EXAFS simulation and refinement. So in copper metal, the first shell is the coordination number of 12 and a distance of 2.54 angstrom. We want to save phases and amplitudes because we want to use them later for EXAFS simulation and refinement, and we just call them copper. Okay, so this is the phase and amplitude. Both files now have been saved and can be used for EXAFS simulation and refinement. Let's start with the experimental copper metal foil spectrum as a proof of concept.
When using experimental phases and amplitude, it's important to make sure that the chi of k you want to use for EXAFS simulation and refinement is no larger in range than the range of the experimental phases and amplitude. Since in this case we use this chi of k to extract the phases and amplitude, the phases and amplitude will be a little bit shorter than this chi of k, so we need to cut a few points left and right of this chi of k for Fourier transformation and EXAFS simulation. So this is the chi of k now we want to use for calculating the Fourier transformation and for EXAFS simulation. So in this tutorial, we want to use experimental phases and amplitudes. So we need to make sure it's the copper K edge, need to make sure the right edge is selected here, and then we can select the phase and the amplitude that we just extracted from the reference copper metal chi of K. So this is only a simulation, so we do not need to bother with the other settings in this box. Okay, those are the starting parameters now, or the parameters for the simulation, coordination number and distance. Those are the crystallographic values that we used to calculate the experimental phase and amplitude, and those have been saved together with the phase and amplitude. Then click on OK, and now we get the simulated EXAFS function in blue together with the experimental radial distribution function of the copper metal foil. Good agreement, but this is no surprise. So now we can use EXAFS refinement and actually perform a refinement using those phases and amplitude to the radial distribution function and get an idea of the changes in the structural parameters that we obtain in this case. So EXAFS refinement now, again, we want to use experimental phases and amplitude. All those settings can stay. The only thing now we need to do is we need to select a range in the radial distribution function. So because we do only have the experimental phases and amplitude for the first shell, we can only perform a calculation and refinement to the first shell of this radial distribution function. We cannot include the higher shells here in the radial distribution function of copper metal. So we select a range that includes only the first shell. Click on OK, and now we can start the refinement. We use the starting parameters that we have here, the crystallographic values. Click on OK, and those are the refinement results. We get the calculated and the experimental radial distribution function here in the R space, and we get a display. As I mentioned, this is no fit in the K space. This is only showing the experimental EXAFS function and the theoretical EXAFS function in the K space. So, okay, and now we can actually calculate confidence limit and the F-test because we want to look at those. So select OK, and this is the calculation. The fit results are being saved in a separate window here, fit results, and there we see, for instance, the number of independent parameters, which is much higher than the 4 parameters that we use. So this is good. We see the ranges. We see the structural parameters, coordination number, distance, the de-Boer-Wöhler factor, and the zero shift with the corresponding values. And we see a correlation matrix. So the significant parameters that we obtain here, coordination number and distance, those are very close to the crystallographic values. In the correlation matrix, we see a correlation between parameter 1 and 3. For instance, this is the coordination number and the de-Boer-Wöhler factor. Again, this is to be expected. Both of those parameters affect the amplitude of the EXAFS chi of k. Same with the distance, so this is parameter 2 and parameter 4. Distance and the zero shift both affect the frequency of the EXAFS function, and those are also correlated. So we have some correlated parameters that now we need to have a look at the confidence limits and see how this correlation that is visible here in the correlation matrix affect the refinement results, affect the confidence limits, and in turn, how reliable are those structural parameters that we have obtained here in this refinement. Confidence limits and f-test are being saved in the history window. At the very bottom here, we see the f-test and we see the confidence limit. F-test also shows correlated parameters. Well, basically, similar to the correlation matrix, we see the Debye-Waller factor and the E0 shift are probably correlated parameters correlated to the coordination number or the distance. And we see the confidence limits, and from the confidence limits, we see that those are small. So we have a narrow range where those parameters can actually vary and not significantly, so in a range larger than 5%, affect the overall fit residual. So in spite of those correlations, which are always present or very often present between coordination number and Debye-Waller factor and distance and E0 shift, so in spite of those correlations, we get narrow confidence limits, and so we can assume reliable structural parameters that we have obtained from this refinement. So next is the experimental chi of k of copper clusters. We select those. Similar to the copper metal foil, we need to shorten the range a little bit, so we just left and right few data points to make sure that the experimental phases and amplitude have a larger range or the same range as the experimental chi of k. Okay, and now we can calculate the Fourier transformation, and we can perform the EXAFS simulation using, again, experimental phases and amplitude, copper K edge, and those are the amplitude and phases that we extracted from the copper metal foil spectrum. Click on OK, we use those values, and now this is the simulated and the experimental radial distribution function. We do see some difference here now because those copper clusters apparently have a lower amplitude, so probably a smaller coordination number. They're smaller clusters than the crystallites in the copper metal foil. And so next step, we can perform a refinement, and same procedure as before. We need to select a range in the radial distribution function that only includes the first shell, and we can start this refinement now. We use the starting parameters for the copper metal. Okay, and we get again a good agreement here between experiment and theory. Again, this is the red trace as the experimental radial distribution function of the copper clusters. The blue is the refined theoretical EXAFS function in the R space and here in the K space. So, okay, and yes, again, we want to calculate confidence limits. And first now is have a look at the fit results. And yeah, as expected, we get a little bit smaller coordination number. So 10.8 here compared to the 12 in the crystallographic value. A little bit shorter distance. A slightly increased disorder parameter and a slight shift in the E0 value. Looking at the correlation matrix, again, we have a correlation between the coordination number and the Debye-Waller factor, and between the E0 parameter and the distance. As I mentioned before, those are very often correlated in EXAFS refinement, and especially those pairs, coordination number and disorder parameter, and the distance and the E0 shift. Those two pairs need to be, you need to be careful with those. Look out for correlation between those parameters in particular. So those are the results. Short note, with experimental phases and amplitude, the disorder parameter that you observe here is relative to the disorder of the experimental phase and amplitude, basically relative to the reference that you use to calculate the experimental phase and amplitude. So here we have in the copper clusters apparently a slightly larger disorder compared to the copper metal foil reference that we used. So in contrast to using theoretical phases and amplitude, where you should not obtain a negative disorder parameter, negative Debye-Waller factor, when using experimental phases and amplitude, this can actually happen. It means that the disorder in your reference is higher than the disorder in your sample. This may be unexpected and may be unusual, but it may not be entirely wrong. So this is possible. Okay, so those are the parameters now that we obtain from this refinement. Let's have a look at the confidence limits and the fit, the F-test. So in this case, the F-test does not indicate a correlation, a strong correlation between the parameters. And here we have the confidence limits, and again, similar to the previous refinement, we get small confidence limits here, so only a small range where those parameters can be varied without significantly affecting the overall fit residual, so again, indicating reliable structural parameters obtained from this refinement. So this is the first try of this refinement. So now we can go back. We want to perform this refinement again and just select some other options in the refinement box. In order to go back to the starting parameter, there is a restore here, and that restores the starting parameters of the previous refinement. So if anything goes wrong with the refinement and you want to start over again with the initial starting parameters, this is what this restore is for. So now we can just perform this refinement again. We go directly to EXAFS refinement. So what we want to do now is we want to have a look at an additional K weighting. So instead of showing the EXAFS function in K space, we want to display another radial distribution function with a different K weighting. So we select at K, K2. So now we, in the refinement, we have two radial distribution functions, one with a K weight of 3 and one with a K weight of 2. And we select show instead of fit. We select OK. We perform the refinement. So now we see two radial distribution functions, one K3 weighted and one K2 weighted. And similar to the refinement in K space, now the EXAFS fit, the refinement, has only been performed to the K cube weighted chi of K, to the right radial distribution function here. The left one is only for display purposes in this example. So it only shows the k-square weighted EXAFS chi of k and the radial distribution function together with the so the experimental together with the theoretical, but this is no refinement results. This is only a display, and we can go on OK. And in this case, no, we do not want to calculate those again. So we can restore parameters and we can perform this refinement again now with not just showing the additional k-weighted radial distribution function, but instead performing the refinement to both radial distribution functions. So performing the refinement to the k-cube and k-square weighted radial distribution function at the same time. So this is now fit. We use the same starting parameters. Okay. And now you see change in color here, blue and red on both sides. And this indicates that the refinement now has been performed to both of those radial distribution function, the k-cube weighted chi of k and the k-square weighted chi of k. So, okay, no, and just briefly restore the parameters. If you want to change parameters by hand, there is an option here to enter the parameters. Again, there are shortcuts, keyboard shortcuts here for parameters and for EXAFS simulation and refinement, and I strongly recommend to use those shortcuts because they really speed up processing of the data. In those tutorials, I always use the mouse, but in practice, I would always use those shortcuts. So enter parameter. This opens just this box, and then you can change those parameters by hand, if you like. Also, just to briefly show this, there is another option here to change parameters. This actually opens this little window here, which permits to changing those parameter stepwise. So you can increase or decrease the coordination number, and you can increase or decrease the distance and see how this affects the theoretical EXAFS function in R space or in K space. This is actually very convenient to adjust starting parameters. So if you want to adjust starting parameters to have them closer to the experimental radial distribution function, then this is a good tool to adjust those values before you start the refinement to make sure that the starting parameters are not too far away from the probable parameters for a good agreement between theory and experiment. Okay, so this is the refinement, EXAFS simulation and refinement using experimental phases and amplitudes. I don't want to prolong this tutorial much longer. Feel free, of course, now to experiment with those settings yourself, change the parameters, change the chi of k range, for instance, select or try to select a shorter range of the EXAFS chi of k, see how this affects the results. In particular, see how this affects the correlation. For instance, if you can increase the confidence limits, well, the shorter the range, the larger the confidence limits will become, and all those things. But I do not want to show those because this is something that you can certainly do now with the data and with what I've shown so far. So this is it for this tutorial. Next tutorial will be about using theoretical amplitudes and phases and perform the EXAFS refinement not only to the first shell, but also to higher shells in the radial distribution function. But enough for this tutorial, and I sure hope to see you in the next one.